This is a production of Cornell University.
Okay, so last lecture was on these crystalline silicate clays, the phyllosilicates, okay? And this is all about soil colloids. So today we're going to talk about the other three soil colloids, and then we're going to start talking about some of the properties of these colloids. Now, when we're talking about colloids at this point, we're talking about really small things, right? Things that are smaller than 1 micron. And I premised the beginning of last lecture with, well, if we're talking about small things, we're really talking about those surfaces. Okay? Remember me saying it's a volume of material, and it's everything's happening at the surfaces. Okay? Well, part of that surface is all about sort of capillary action, you know, water movement and things like that. But part of that surface is about the charge. And that's what we're going to be talking about later on in today's lecture. First, let's finish talking about what these colloids are. And the first one we're going to talk about is non-crystalline silicates. Phyllo means sheet. So these are phyllosilicates. So when I say phyllosilicates here, I misspoke. These are still silicates, the same ingredients that are in these, but the way they're formed is very different. These are basically volcanic products. Okay? They're coming from volcanic ash. And you can imagine, as this magma is cooled slowly, I'm going to be able to form large crystals. But if it's a magma event that's actually becoming ejecta, or it's coming up very quickly and cooling very quickly, the regular crystal structure that you get with the phyllosilicates is not going to happen. But I am still going to get the same ingredients. I'm basically cooking it at a different temperature, sort of. Okay? So the parent material is basically the same, but the nature of the parent material is different. It's composed largely of vitric or glassy materials containing various amounts of aluminum silica, and it lacks the well-defined crystals that you're going to get from these slower cooled environments. Okay? Aliphanes and amygdalites are the common early stage residual weathering products of this stuff, but it's basically this glass and these poorly ordered structure, but it's basically just weathering out, and it goes into these aliphanes and amygdalites. The aliphanes form inside the glass fragments, okay, where the silicon concentrations and the pH are fairly high, and they have a characteristically sort of spheroidal shape. And I'll show you some pictures of these in a moment. The amygdalite tends to form on the exterior, okay, of these fragments, and they're in an environment where there's lower pHs and lower concentrations of silicate, and they tend to have sort of like a thread-like. Here's some pictures of it. Here's the aliphanes, sort of the spheroidal stuff that's forming inside. Here's the amygdalite. Okay, this is a very small. So this is 2 microns right here to give you a scale. Okay, this is an entire particle. This is these amorphous materials. You can imagine that being a ejecta of volcanic material, right? Okay, there's the scale. That's 10 microns. I also put in here. This is vermiculite, and this is smectite to give you a sort of a scale, a sort of a comparison. Okay, these are these phyllosilicates. Okay, these are these amorphous materials. So you can see that they physically look different. They're not just morphologically, they physically look different. Okay, the next one is iron and aluminum oxides. We call these Sesquioxides. Okay, they're dominantly gibbsite, which is the aluminum oxide, and goethite, which is the iron oxide. Okay, they're found in many, many soils. I mean, we find them around here. We find them basically everywhere. Okay? They're especially important in highly weathered soils in the warm, humid tropics. Okay, why? Well, these guys tend to be the end products of weathering, and so we find a lot of them. Now, you guys remember me actually, next slide. Remember me showing you slides of this stuff. These are those oxasols. The reds that we're seeing in here are due to these goethite iron oxide types. Not strictly goethite, but these iron oxides. It's that red, it's the rust. Okay? They consist mainly of either iron or aluminum atoms attached with or coordinated with oxygen atoms. Okay? This oxygen is often associated with a proton to make hydroxyl groups, and that term right there, that's going to become more important later in this lecture. So keep that in mind. Okay? Some, such as the gibbsite and goethite, form crystalline sheets. They can, in fact, form sheets. And you saw that in that one module that I showed online. When you guys go click on it, okay, how the 2 tetrahedral sheets sort of separate off and the octahedral sheet is left behind. Okay, and they also can form amorphous coatings. You've seen these amorphous coatings. These are those redox features that we saw when we were up at Mount Pleasant. Okay? Now, because of and this is where this hydroxyl component comes in important, because of this surface plane of the covalence, basically because of where these oxygens are, they're exposed to the soil solution. They're exposed to the soil solution. They're not actually attached to another crystalline sheet. Because of that, these protons are bonding. Now, you guys remember, I sort of mentioned this earlier on when we were talking about these structures, when I was talking about the building blocks. But I started by drawing an octahedral sheet here, okay, and it has a couple more coming out, okay. But this guy is not going to live like this in solution because this is going to be a charged particle, right? Okay, and if it's a charged particle, all of these oxygens that are out here are going to have a proton attached to them. Okay, now I could have a larger sheet that keeps going on out here, but all of the oxygens that are at the edge are exposed to that soil solution, and they're going to have a proton attached to it. Okay, because they want to balance that charge. Okay, now because of this proton in here, remember me saying earlier that these charges with isomorphic substitution, they tend to have a net negative charge. But because this proton is attaching to this hydroxide, these Sesquioxides actually tend to have an anion attraction because they're, in a sense, positively charged. Now, the positive charge is coming because a proton is attaching to them. It's not part of the crystal. Okay? But it's a positive charge, which means negatively charged ions are going to be attracted to this particle. Does that make sense? Keep that in mind because we are going to be talking about it later on. Okay, this is what these things look like. Here's a gibbsite and there's a goethite. Actually very pretty. This is these are related to fool's gold. Does anybody know fool's gold? Iron pyrite. Okay, very similar. Okay, they can form rather large structures. But these are variants of gibbsite and goethite. Okay, they also have these amorphous coatings, and these should be familiar to you guys. This is what you guys saw. I mean, I've showed you this slide before, but this is what we saw down at the bottom of Mount Pleasant, or that valley in Mount Pleasant, right? Okay, iron accumulations, amorphous, not crystalline. Okay, the next colloid. These are organic, humic colloids, organic molecules, okay? They're important in nearly all soils. Organic matter is really important for a lot of reasons, okay? They are not mineral and they're not crystalline. I mean, they're organic, okay? They consist primarily of long convolvulated, can anybody say that? Convoluted, that's the word. They consist of long convoluted chains and rings of carbon structure, okay, that are bonded with hydrogen, oxygen, and nitrogen as well as other nutrients. They are very high capacity to absorb water, and they have high amounts of both those positive charges as well as those negative charges, okay, though their permanent charge is still always negative. The net negative charge is negative. Okay, now this is again that molecule that I showed you yesterday. Or Monday. This is not a real molecule. This is just a model of an organic molecule. But you can see how complex it is. And what's important here is all these hydroxyl groups that are in here that are exposed out into the soil solution. They behave very similarly to those hydroxyls or those OHs that are on the Sesquioxides. And this is where, depending upon what the pH is of the soil system, this is where you potentially will have anions attracted and held in from the solution on the soil. Okay, now scale here, this is an organic molecule. Okay, here's 2 microns, so basically half of that is basically colloidal size. And this is obviously larger than colloidal size, but if you look at the internal structure in this, we're definitely at the 1 micron size. Okay, so yes, while the particle itself may be in fact much larger than colloidal size, it is in fact still reacting with the colloidal material. And in reality, this is just a very large piece. This stuff can be degraded and become really small. So it's in fact really is colloidal material. Okay? Questions so far? Cool. All right, so we have this very large complex organic molecule. In a sense, it's very important because of the surface area, but in a sense, part of why it's so important is because of these things that are sticking out into the soil solution. Okay, we have carboxylic groups here, the COOH. We have phenolic groups, the ring structure with the OH, and we have hydroxyl groups, basically the OH. Okay, all of these OHs, all of these O's, I should say, these oxygens, can react with the proton and change the charge of the entire molecule. All right, so if this is a high pH or a low pH, that proton may or may not be there. If it's a high pH, this proton's not going to be there, and in essence, it's going to create give this molecule a more negative charge. At low pHs, the proton is going to be there, and it's going to give the molecule a more positive charge. Does that make sense? So the charge on these hydroxyls are pH dependent. Okay. So those are the 4 types of phyllosilicates. We have I keep saying this. These are the 4 types of colloids. The first one is the crystalline phyllosilicates. The second one is those amorphous ones. The third is the sesquioxides, and the last one is the organic. Okay? Cool. Take a deep breath. You made it through that component. Any kind of questions? Go.
This has been a production of Cornell University, on the web at cornell.edu.